Hello. In this video, we're going to talk about antiderivatives. So the motivation comes from the question, if we know f prime x is equal to 3x squared, what was the original f of x? So take a second to think about it. If we knew f prime x was 3x squared, what would be fx? Now the answer is that f of x would be equal to x to the power 3. And that's very clear because the derivative of x to the 3 will be 3x to the power 2. So that's sort of our guiding question. If we know the derivative, how do we find the function we started with? Now if we look at a definition here, a function capital F of x defined over some interval I is called an antiderivative of f of x if the derivative of capital F of x equals f of x for all x in the interval I. So in our previous example here, x to the 3 would be an antiderivative of 3x squared because the derivative of x to the 3 is 3x squared. Now the notation we're going to use for antiderivative is d to the power minus 1. So let's try an example here. If f of x is equal to 4x to the 3, what will be the antiderivative of f of x? Well, we would think about it for a little while, and we would realize that one answer would be x to the power 4. And we could say this is true since the derivative of x to the power 4 is 4x to the power 3. Now if we notice, we can use the same logic to say that the antiderivative must be x to the power 4 plus 7, since when we take the derivative of x to the 4 plus 7, we still get 4x to the power 3. Now let's think about this. Both x to the power 4 and x to the power 4 plus 7 were antiderivatives of 4x to the power 3. And so this is noted here in above. Each capital F of x differ by a constant. This is actually going to be a theorem we can prove. So the theorem states, if f1 and f2 are two antiderivatives of f of x on some interval ab, then f1 and f2 differ by a constant. So let's look at the proof here. So we're going to suppose f1x and f2x are two antiderivatives of f of x, and we're going to let g of x equal f1x minus f2 of x. Now, when we investigate the derivative of g of x, we find something very interesting. G prime x equals, well, the derivative of f1, since it's an antiderivative, is just f of x, and the derivative of f2 is also f of x. So we find that the derivative of g of x is going to be 0 for any x. Now what we can do is apply the mean value theorem. So we're going to do the following. By applying the mean value theorem to g of x on, and we're going to consider a subinterval here, on the subinterval, the subinterval a to x, we get the following. We get g prime of c has to equal g of x minus g of a all over x minus a, where c is in a to x. Okay, now if we look at this here, the denominator is not 0, but g prime of c has to be 0, because g prime of x is equal to 0 for any x. So in particular, it is equal to 0 for c. So we have to have here 0 equals g of x minus g of a over x minus a. And that means, therefore, that g of x minus g of a has to equal 0, or another way of saying that is g of x has to equal g of a. Now, if g of x equals g of a is just a constant, and so that means that g of x is always equal to the same number. It's always equal to g of a. What that says to us is that g of x, this function here, is actually just a constant. It's actually just equal to g of a. If we go back to our original definition of g of x here, that means that this left-hand side will have to just equal a constant. So we're almost done the proof now. We can rewrite this statement here, g of x equals f1x minus f2 of x. We can take the f2x to the other side, and we will have f1x equals f2x plus g of x, where g of x is a constant. And this proves the theorem. We have shown now that f1 and f2 both differ by a constant, the constant g of x. So remark, using the above theorem, we can redefine the antiderivative. So our new definition is as follows. A function, capital F of x plus c, where c is a constant defined on some interval I, is called an antiderivative of f of x if the derivative of capital F of x plus c is equal to f of x for all x in the interval. So this says that our antiderivative is more general. It's going to be a function, but there's always going to be some constant added to it. So this is going to give us some very nice rules for finding antiderivatives. So the first rule here for finding antiderivatives, let's let k be a constant. The antiderivative of k will be k times x plus c. So let's take a look at this example. Suppose we have the antiderivative of 7. Well, that will be equal to 7x plus c. And of course that is true, since the derivative of 7x plus c equals 7. When thinking about antiderivatives, we want to find the answer so that when we take the derivative, we get back to where we started. Let's take a look here at Rule 2. Rule 2 says that the antiderivative of a power of x, so x to the power n, will be x to the n plus 1 over n plus 1 plus c, where n is not equal to 1. So let's see this in the example here. If we wanted to find the antiderivative of x to the power of 100, we would add 1 to the power, and we would divide by the new power, and we would add a constant c. Let's take a look at the next example. We have the antiderivative of 1 over the square root of x to the 3. So we're going to want to rewrite that as an actual power. So that will be x to the minus 3 over 2. Using our rule, when we add 1 to the power, we get x to the minus 1 over 2 all over minus 1 over 2 plus c. Let's take a look at Rule 3 here. Rule 3 says the antiderivative of a constant times a function. We can take that constant out, and we just have to consider the antiderivative of the function. So here we have e and 1 over the square root of x. So again, let's rewrite that as the antiderivative of e x to the minus 1/2. And now we want to factor out that constant. We want to take the e out in front and just consider the antiderivative of x to the minus 1 over 2. We have to add 1 to the power, so we will have x to the 1/2 over 1/2 plus c. The next rule says that if we take the antiderivative of two functions added together, we can just consider their antiderivatives separately. Or the antiderivative of a sum is the sum of the antiderivatives. So here we have to consider an antiderivative. Well, if we just look at the antiderivative of x to the 3, and we can also factor out the 9 here, and just look at the antiderivative of x to the 2/3. That will be equal to, we add 1 to the power, x to the 4 over 4, plus 9, x to the 5 over 3, over 5 over 3, plus c. Now let's take a look here at Rule 5. Rule 5 says that the antiderivative of a difference is the difference of the antiderivatives. So let's go ahead and do this one here in one step. This will be 4 x to the, we have to add 1 to the power, which will give us a negative 8, over negative 8, subtract 8, x to the 1.7 over 1.7 plus c. Now, in general, you can calculate antiderivatives of any sum one at a time. So let's say we had the following question here. We have the antiderivative of minus 2 pi, 1 over x to the 3, 5x to the 7. We're just going to do these one at a time. So first I'm going to want to rewrite this here, having them as powers. So this will be minus 2 pi plus x to the minus 3 minus 5x to the 7. And now I simply need to take the antiderivative of each one at a time. Minus 2 pi is a constant, so it will be minus 2 pi times x. This is a power, so I add 1 to the power and divide by my new power. Here the constant doesn't matter, it gets factored out. I add 1 to my power, divide by my new power. And always remember to add c. Rule 6 is actually a lot of rules in one. The idea for Rule 6 is that anytime we used to know a derivative, we have a corresponding antiderivative. So since the derivative of sine x is cos x, we now know that the antiderivative of cos x is sine x. Or since we know the derivative of negative cos x will be negative sine x, or just a positive sine x, we know the antiderivative of sine x will be negative cos x. So each one of your derivatives gives you an antiderivative. And again, the way to remember these antiderivatives, for example, if we were to say, ask ourselves what is the antiderivative of 1 over 1 plus x squared, is to ask ourselves, if we were looking at this antiderivative here, we'd ask ourselves, what function has derivative 1 over 1 plus x squared? That's the question we ask ourselves. And if we can remember that the answer is tan inverse of x, then we have our answer. So I would encourage you here to take a look at all of the different antiderivative rules. They're all based on the derivative rules that we know. So take a look at the antiderivative rules, and they're not new rules to memorize, but they're just reminding us of our previous rules. So let's try an example here. Suppose we want to find the antiderivative of the following big group of functions. How would we do that? Well, we would have to take the antiderivative one at a time. Now the antiderivative of sine x, we have to think to ourselves, what gives us a derivative of sine x? Well, it will be negative cos x. Now I put the negative 2 here and ask myself, what gives me a derivative of cos x? The answer is sine x. What gives me a derivative of secant x tan x? The function I'm looking for is secant x. And what gives me a derivative of e to the x? Simply e to the x. And when you're finished your antiderivative question, always remember to add plus c. So let's take a look at the following challenging antiderivative. We have the antiderivative of 2 pi over the cube root of x minus 3 secant squared x plus 7 over x. So it's often very helpful in these problems to rewrite the question with exponents. So this is 2 pi x to the minus 1 over 3 minus 3 secant squared x plus 7 over x. We can actually leave the 7 over x because it's easier to identify in that form. Now the antiderivative here will be 2 pi is a constant, so it just comes out. We have x to the 2 over 3 all over 2 over 3. Subtract. Again, we think to ourselves, what is the function that has derivative secant squared? The function is tan x plus 7. And what's the function that has derivative 1 over x? It is ln x. And we need to put absolute values on the x. Plus c. Okay, in this example here, we have a function multiplying another function. And so in this case, we should probably multiply this out to try and take a look at what's going on. So we have the antiderivative of 2 cosecant x cotangent x minus 5 cosecant squared x. And by multiplying it out, we can clearly see that this first term here, the function that gives us this as the derivative, is negative cosecant, and the function that gives us this as the derivative is negative cotan. So we will have 2 negative cosecant x minus 5 negative cotan x plus c. And it's up to you whether or not you want to clean up the negatives. Let's take a look at the next example here. We have the antiderivative of some strange functions. And again, we need to remember our derivatives. What function has this as a derivative? So we think back, we think to ourselves, this looks like one of those inverse trig functions. In fact, it's sine inverse of x plus 7. And really we want to think about this here as 7 times 1 over 1 plus x squared, so that we can see the answer is 7 tan inverse of x plus. And for any time you have a number with x being the power, it's handy to have the rule memorized. It's 6 to the x over ln 6 plus c. So your homework for this unit will be 1 to 22. You can omit 19. These are on page 355. Thanks for watching.